Welcome to Yaka Digital Network. In Senior 4, geometry moves away from the flat surfaces of a page and enters the spatial realm of 3 dimensions. Solving these 3D problems requires a shift in perspective. Instead of looking for new formulas, the objective is to learn how to isolate specific 2-dimensional shapes within a 3-dimensional volume. Take, for example, a telecommunications mast standing in the center of a rectangular concrete compound in Kampala. We can model the compound as a 2D plane. If we attach a support cable from the top of the mast to one corner of the base, we create a line that exists in 3D space, intersecting that plane at a single point. If the sun were directly overhead, that cable would cast a perpendicular shadow onto the concrete. This shadow is called the orthogonal projection of the line. Identifying this projection allows us to define the specific angle between a 3D line and the flat surface it meets. Let's convert this scenario into a geometric diagram. We'll label the base plane A, B, C, D, the center point E, and the peak of the mast V. Our support cable is the line VA. In this model, the height of the mast, VE, is 5 centimeters. The distance from the center to the corner, EA, is 4 centimeters. We are looking for the angle where the line VA meets the base plane. Because we are representing 3D objects on a 2D screen, angles often appear distorted or skewed depending on our viewing angle. To solve these accurately, we must rely on geometric properties rather than visual estimation. Since the post VE is vertical and the segment EA is on a horizontal base, they meet at a right angle. This confirms that V, E, and A form a right-angle triangle. To simplify the math, we can extract this triangle from the 3D model. This lets us treat the 3D problem as a standard 2D trigonometric calculation. We need to find the angle theta at vertex A, which represents the slope of the cable relative to the ground. We have the side opposite the angle, which is 5, and the adjacent side, which is 4. Take a moment to consider which trigonometric ratio applies here. Using the SOH-CAH-TOA principle, the relationship between the opposite and adjacent sides is defined by the tangent ratio. Our equation is tan theta equals 5 divided by 4, which gives us a ratio of 1.25. By applying the inverse tangent function, we find that the angle is approximately 51.34 degrees. By isolating the orthogonal projection and extracting the 2D triangle, we can solve for the spatial relationships within the solid shape. This framework solves 3D solids consistently. First, sketch the shape. Second, identify the projection. Third, extract the triangle. And fourth, apply trigonometry. This same logic also finds the dihedral angle between 2 planes by identifying lines perpendicular to their intersection. Proficiency in 3D geometry is built on the systematic identification of orthogonal projections and the reduction of spatial volumes into solvable 2D components. To practice more 3D scenarios and prepare for your examinations, join the full course at Yaka Digital Network.